All right, so here's what this is. Final lesson. This is from about, what, '02 maybe? 2002? It's called Microteach, where we had to teach in front of our college classroom. This girl up front here, this girl right here, really liked frogs. That's what I remember. So we'll just watch this. First time I've seen it in probably 12 years. I don't know.
So, Isaac Newton came along, and he came up with three laws, and in the next few lessons we'll talk about each one of those laws. His first law, second, and third. Before we talk about Newton's first law and get the definition of it, I think it's
yes, it is on VCR.
A couple demonstrations that will help understanding the law when we read it on the board. Okay, the first demonstration is have a golf ball, which is the game of physics, basically. And I take the golf ball and I set it on the table. This is a back table. Okay. Can anybody tell me what it's doing? Sitting still. Okay.
It's a VCR recording too. It's pretty bad.
Demonstration involves a piece of cardboard. This is for the people in the back if they can't see the demonstration going on. It's a cardboard. It's like a foam piece of cardboard or something. And we have a quarter on top of it. And the arrow means that I'm going to hit the cardboard, and we'll see what happens to the quarter. So, I place it on my hand, quarter on top, hit the cardboard, quarter, still in my hand. That's the second demonstration. The third demonstration involves two cars. My BMW SUV. Okay. And we'll place a quarter on each one. And I will move the cars together and let go. And we'll see what happens to the quarters. So we get a quick drawing of that. That's a car. And we have quarter on top. And we'll go together.
There's a bunch of future elementary teachers too.
Everybody see what happened to the quarters? To the cars? What happened to the cars? Just do it again. Okay, you can do it again. Pay close attention to what the quarters do and what the cars also do. The cars
bounce back. Quarters.
right? Theoretically, what would the cars have done if when they hit? They would have stopped. Okay, and then what did the quarters do? They stayed in motion. So now, Newton's famous book Principia, and I've stated there, he stated his three laws of motion. And his exact definition of his first law of motion, can everybody see first? Okay. His exact definition of his first law of motion is that every body preserves in its state of being at rest or of moving uniformly straightforward, except insofar as it is compelled to change its state by force impressed upon it. Now, I don't know about you. Personally, reading this definition, I'm a little confused myself. So, what we did, or I did, was simplify the definition to something I thought would be better understandable. And that is that every object continues in a state of rest or of motion in a straight line at constant speed unless acted upon by outside force. Now, does everybody agree with me that this is a little easier to understand? Okay. Even from there, we could break this law down into two parts. And the first part is that an object at rest stays at rest unless acted on by an outside force. Now, a good example of this is when I get home from school every day, I take my shoes off, I set them down by the door. And what happens when I get up in the morning, I want to put them back on? Where are they at? Right there. They haven't moved. No force has been acted upon it to make it move. Second part of Newton's first law is that an object in motion will stay moving in that motion unless acted upon by an outside force. Now, a good example I think of this is when I'm playing air hockey I get in air hockey, I like air hockey. So I'm playing air hockey, and I'm hitting the puck, and it's sliding. And it moves in a straight line until it hits the wall, or the side, and then it moves in a straight line from there. So it moves in a straight line, nothing is affecting it until it hits the wall. And once it hits the wall, another force is applied to it, which causes it to change direction. And then from there, it moves in a straight line until another force is acted upon. So now, I'd like to go back to the demonstrations, and we're going to look at the motion of the objects for the demonstration I did before, and state what the motions are, and state which part of the law, either the first or second part, governed the motion that we saw. So, could somebody please tell me what the first, with the ball sitting on the table, what part
We'll
of the law?
skip forward here the best we can.
And why?
Let me see here. Old VCR. I had a lot more hair. I was quite a bit wider. That girl messed it up, the demonstration, I do remember that. She looked very happy. The girl that liked frogs. Kindergarten, she did her lesson in kindergarten. She brought a laptop every day to class. I don't remember anybody else in the class. I think those are black pants. They're supposed to act like high school kids, whatever that means. Oh, come on, let's get to the next one here. Must be reviewing. Let's stop this and see if we can go. Oh, there it goes. Oh, I got different pants on.
Motion. So, as for review, about that today. Does anybody remember anything about cars? Anything like that? Right? Right, it kept moving.
That's a lot more hair.
It takes place in the direct line. Is proportional to the amount of force pressed and takes place on direction straight line. So basically what this law states is that an object in motion, when acted upon by an outside force, will move in the direction on which the force is applied. And a good way,
Which is not exactly true.
is you jaw roll the ball, okay, and you just hit the ball.
Do you remember that kid?
Something like this. I take it easy so you don't hurt anybody. See, and he applied a force in this direction. And what way did the ball move? Exactly. That's the force I just. Okay. So now, good examples of this is maybe when you're golfing or playing baseball, the ball's sitting there, it's at rest. When a force is applied to it by the golf club, it moves in the direction, the inclination of the golf club, so it moves in a straight line. It's acted by gravity, but we neglect this simple things in physics sometimes to make it a lot simpler. So, baseball, the ball's pitched, it's moving in a certain motion. Player hits the ball, hopefully, and the ball moves in which in the direction which the force is applied. So, when what happens when the force is applied? Does anything else occur? Like with maybe the velocity of an object, the acceleration? And yes, it does, and that's what we'll do today. Instead of just giving you the law, or the equation that goes along with the second line, I think it's important that we build a law by adjusting variables with our air track here. And the air track just helps to eliminate friction because it's riding on a cushion of air. You can tell that this is a slide too long. So, the equation that we learned earlier on in earlier lessons is that V, which is our velocity final, is equal to V0 plus the acceleration times time. So we have velocity final is equal to initial velocity plus the acceleration times the time. And that would be important because in our demonstration, the initial velocity will be 0 because it's at rest. And that makes perfect sense. So if the velocity is increased, what would happen to the acceleration? Anybody have a clue there?
Elementary teachers.
Did it increase? Exactly. Time does not really play a part in what we're doing today, but as the acceleration is increased, the velocity is increased. So that'll be good for future reference while we're doing the experiment or demonstration. So we have three variables that take place in this demonstration. We have force, we have acceleration, and we have the mass. The mass will take place right here. This is our mass. The acceleration, or the velocity actually, and we could relate that to acceleration later on, takes place along the track, and then we have a force being applied to it over here. Okay? So the first part, we'll keep the force constant. And in the second part of the experiment, we will keep the mass constant. So, first one. Now, I'll turn this on, it gets kind of loud, so hopefully.
People help me, friends of mine help me carry this across campus.
I'll run the first trial. The force will stay constant for the second trial also. I won't add anything to it. We'll just add mass to this and we'll see what happens to the acceleration. Actually, I'd like to volunteer if you don't mind. Need somebody to hold that, just the top part right here, to keep it from moving. And actually that'll be fine. Just one first. So I'll turn this on. Pay attention to the acceleration of the velocity of the glider. Let's do one more time. Finish on.
Must be adding mass to the hook.
Now we have 200 grams here. Magnitude or glider. So this makes our glider more massive. Now, you saw the velocity of it on the first trial. Let's try to pay attention to what happens this time and see if it's any different. Yeah, hold that. One more time. And somebody tell me what happened when the mass was added to glider. It's like take longer to speed up. Did it slow down? Acceleration was slower. Okay, so force was constant. Big term is proportional. Proportional means when, like this, A is proportional to B here, because when B is increased, so is A. But now we have acceleration.
Probably still wear the same shoes.
Acceleration slows down.
Maybe
mass
not.
is increased. So it's called inversely proportional. Because let's say our mass is 1. What would the acceleration be? 1. Let's say the mass is 2. Acceleration would be
They don't know. They don't know. 1 over 2 is a half.
what's 1? What's 1 divided? It'd be 1/2, so the acceleration would actually slow down. Or would slow down. So now let's take these masses on. Apply the same force one more time. Because our mass will stay constant. We won't add any mass to the glider. So let's run this one more time, Sean. So
still do this.
Right. So, once again, we have our acceleration is proportional to what? What did I increase over here? That made the acceleration also increase.
Oh, this is painful.
Mass was constant. Acceleration increased.
Oh.
The variable was actually just force.
Should have wore the white shirt first. I don't know why I didn't. With the light pants. It was kind of everything was bigger back then. Especially if you weren't like super skinny.
But mass times gravity is equal to weight, which is a force. So gravity and force are very, very relatable.
Wait, did I make a hand sign there? What was that? What was that? I'd be saying awesome blossom now and all kind of junk during this thing.